Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, it's a great pleasure to introduce Christian Wimmer. Christian is a postdoctorate researcher at UC Irvine with Michael Franz. He's been there 2.5 years. And before that, he got his doctorate at Johannes Kepler University in Linz, Austria. Christian has worked on virtual machines for quite a while, also contributing the linear scan register allocator to the HotSpot compiler. And today he's going to be talking about optimizations for virtual machines. Welcome.
Yeah, thank you for the introduction. I'm very happy to be here with you today and talk a bit about my work. Both what I did in Linz, in Austria, and what I am currently doing in Irvine, in California. So just to give you a brief background, as Ben said, I did my master and PhD in Linz, in Austria. We have a long-standing collaboration there with some microsystems, now Oracle, working on the HotSpot VM. So that's a project that started in 2000 and it's still ongoing. And so much of the work I'm talking here is was done inside of HotSpot. That's not because we think that's the best or the greatest technology. That's just, yes, when you get the money from some source, you have to do it in that product. So, but I think the general ideas are applicable to everything. So you can substitute Java with whatever language you want. And we're talking about dynamic languages. So in Irvine, we have a collaboration with Mozilla. So we are using their JavaScript engine there to do research. But in general, I want to talk about feedback-directed optimistic optimizations in virtual machines. So basically, I really believe that the VM-based execution model should be the future because it really allows you to adjust, optimize inside the VM and to get runtime benefits for all applications running on top of it. You can get security benefits. So having a VM as the underlying thing shouldn't be seen as an obstacle or it hinders you and makes everything slower. I think it's really a mean to make things better and faster. So on that slide, there is a collection of things that we worked on in Linz and in Irvine. And the two things I want to talk most about in this talk is first, automatic object inlining. That was basically my PhD thesis in Linz. So I will go briefly over that and tell you what I did to optimize objects in the heap on the fly at runtime. And then I'll switch to Treys-based compilation. That's one of our projects in Irvine, where we do that for Sun Labs Maxine virtual machine. So, optimistic optimizations, why are they so great and what can you do? And one of the best examples or oldest examples for doing optimistic optimizations is when you do inlining of virtual methods. When you have a language like Java, where basically every method call is per default virtual, so you have dynamic binding as the default, you cannot do aggressive optimizations when you just look at the language semantics, because even when you have a class A that has a method getX and you call that method, you cannot just inline the method getX in the method foo here, because what can happen, you can load another class B at runtime later on. That class B can be transferred somewhere over the network, so at the first, when you start executing the system just with method foo in class A, you don't even know that class B exists in the world, so you cannot plan for it to be loaded. But it can be loaded and it can override the method getX. And so when you inline that method into method foo, apparently after loading of class B, that is wrong, because now you really need a dynamic method call, dynamic binding to get into the right method. So what's the solution for that? We want to inline it. So when the method foo is compiled at first, when only class A is here, just inline it. But collect some metadata that you said, oh, I inlined that method. And then when you load class B, just look at the metadata and say, oh, I did something wrong when compiling foo. From my current point of view now, it's no longer valid to inline it. So just discard the meshing code of foo and recompile it later without the inlining, or inline both methods if you think that's worthwhile. So if the profiling thinks that should be done. But we have a problem, because there can be the corner case that the class B is loaded exactly at this point. So you are in the middle of method foo. So what do you do in that case? You're already executing the optimized meshing code. And that's the point where deoptimization kicks in, that you can say, oh, I did something wrong, and I have the unfortunate corner case that I'm running a wrong method now. Let's switch back to the interpreter just in the middle of foo, and it's really expensive to reconstruct the interpreter stack frames for the inlined methods and do all that fix-up work. No one ever optimizes for that case, because in practice it doesn't occur. But you have this really cool safety net that you can switch back out of your optimized code back to the baseline code, back to the interpreter at any point of time, and use that for optimizations. And why do we have no problem with that? Because most classes are, of course, already loaded when you compile a method the first time, because when you have an interpreter or some baseline compiler executing the first 1,000 iterations of invocations of a method, then basically you already reached some sort of stable state. So most classes are loaded, and it's really only a safety net. What can you do with that? So one example what we did is for the HotSpot VM, we implemented Aerie bounds check elimination in an optimistic sense. So that's a short loop, basically the meshing code of that not really interesting method. But you have Aerie bounds checks in Java, in .NET, in every managed language, and which means you have to check the Aerie bounds before the access happens. So which means you have the compare and the branch inside the hot loop, and you want to get rid of that. How can you get rid of that? You can do some static analysis if you want, and check if the parameter c that comes in is always below the array length. But that's an interprocedural analysis, and we don't really want to do that, because it's really complicated. You have to analyze everything that could call the method clear. So it's much better to just optimize for the common case that c is below the length of a, and just move that check out of the loop and check before the loop that c is below the array length, and we are fine. So we want to move that check, but unfortunately we cannot just put in the check and throw an exception, because managed languages have this tight specification. And yes, that's a good thing that you have a good a tight specification. So you cannot throw an exception at the place at some time earlier and say, oh, something will go wrong most likely in the future, let's throw an exception. So what can we do? Just don't throw an exception. Just deoptimize and go back to the interpreter. So at this point, reconstruct the interpreter state, execute the loop really slowly in the interpreter until the point is reached where the exception should be thrown, and the interpreter then throws the exception. So deoptimize, preserve the exception semantics, and we have exactly what we want. We have no check in the hot loop. We have no sort of code duplication. everything is fine. So you do the aggressive optimization without really worrying about what could happen in the future. And if it turns out that you have a really bad program that throws the exception frequently, yes, then we can recompile the whole method again and do the check inside the loop. But that's unlikely to happen. So that's one use case of the optimization, and the reason why I'm stressing that much is I used it quite heavily for my automatic object inlining. What's there basically the idea? You have object-oriented programming language, so you have your programming style with you have your data object, you have your collection class. In case of Java, it's Aerie list, and it uses an Aerie to store the real data. So you have lots of small objects floating around. But what you really want is when you have a pointer to a polyline object and you want to access one of the points that's stored in that array. And if the case that you really want is you want to do that with one memory access, that you just say, I have my pointer, and I have the index of the array that I want to access, and just do some magic address computation and do one load to load that. And that was basically what we achieved by grouping that object together in the heap dynamically at runtime. So with no analysis before the application is started, no interprocedural global static analysis inside the VM, just do everything on the fly based on profiling information, dynamic optimization in the garbage collector, in the JIT compiler, and having the safety net of the optimization means you don't have to worry about what's happening in the future. When you have dynamic class loading that violates some invariants, just go back to the unoptimized meshing code. And we did it for the HotSpot VM. That's just the system structure. It's not a real surprise. I think most VMs look somehow that way. HotSpot VM has an interpreter, but if that is a baseline JIT compiler, it wouldn't really change much. We have the JIT compiler that optimizes the bytecodes, and that's basically this deoptimization loop back from the meshing code to the bytecodes so that you can go back. And the basic setting for the client VM setting has a generational garbage collector with 2 generations, stop and copy collection for the young generation, and the mark and compact collection for the whole heap. So every now and then a mark and compact just processes all generations at the same time. So how can we do this automatic object inlining? That's basically the flow of the steps that are taken for every field that basically every field of every object. At first, we insert read barriers. That means every read of a field is instrumented with a counter because we don't want to optimize fields that are rarely accessed. So first we have to find out what are really the frequently accessed fields. So just count all field accesses. And that's the first bailout if a field is not hot. So after a certain measurement interval, if the counter is still low, just get rid of the read barrier again, recompile the method without the counter in, and forget that field forever. But if that field is hot, then it's important, and we can we can tell the garbage collector now, yes, we know we have these 2 objects that are connected by a hot field. Please try to put these objects together. That's just a hint at first to the garbage collector, and the different garbage collection algorithms look at these hints and see if it's possible to do that. And if yes, then they co-locate the objects. That's a first good step because it improves the cache behavior. But it's not really enough to eliminate the field access. That's our final goal, because just hinting the garbage collector to do something in most of the cases doesn't guarantee that the objects are really always at the co-located. So we have to do some additional steps to guarantee co-location. the first thing is that when we allocate new objects, so when we allocate a new polyline and a new Aerie list, that the allocation is really done atomically, so that new objects are properly collocated. Then, since we are in a completely dynamic system, we have to make sure that the field is not overwritten later. So if you have a field that is overwritten, so when a field can point to multiple different objects during its lifetime, then it cannot be collocated to all of these child objects. So we have to prevent that by instrumenting field stores and saying, if a field store happens, deoptimize. Then we have to wait for a full garbage collection. That's basically to clean up all the objects that are not collocated yet in the heap. So full garbage collection means really all generations are processed. So after a full garbage collection, you really have the guarantee. And then we can really optimize our field accesses. And as you can imagine, that's the easiest part of it, because that's then done in the JIT compiler and just eliminating a field access and replacing it by address arithmetic in the JIT compiler. That's a very simple transformation. And at all of these points, we can still reach this inlining failed state. So it can be possible that the objects cannot be allocated together. It can be that the field store guard fails at runtime. It can be that the garbage collection cannot put the objects together. In all these cases, we just don't optimize the field. And yes, it can also happen that the later class loading invalidates this. So you just load another class later that invalidates one of the invariants. And in that case, also de-optimize.
I have a question about the way you consider things hot. So are you looking at individual pairs of objects, or are you looking at the class? Is the field considered hot for the whole class?
It's for the whole class.
Okay.
That was one of our early implementation decisions to do it on a per class basis, because doing it per object in HotSpot would be too much overhead. You cannot really track it per object. That's one of our biggest limitations. And yes, if I would do it again, perhaps I would do it on at least not on a per object basis, but try to group certain objects together so that you can have some partitions of a class. That would certainly be helpful and increase the amount of objects that can be optimized. But in our system, it's on a per class basis. So the whole class is optimized or de-optimized. So the next slides I want to go over rather quickly. That's just to show you these steps in a bit more detail. So basically, that's again our example that we saw before. We have the polyline class that references a list of points. That's basically the Java collection class Aerie list, which uses an object array to store the element. And read barriers are inserted in the meshing code by the compiler. So when the method is compiled the first time, all field accesses are instrumented with the read barriers. And since it's done in the JIT compiler, it's really an increment of a point of an address that's at a fixed address, a counter at a fixed address, so a simple increment instruction. And then these counters are checked at regular intervals. Yes?
Why did you do this in JIT and not necessarily during interpretation?
2 reasons. First, the interpreter would have to do a lookup for the address for every field access. That would be complicated, but it's doable because the interpreter is slow anyway. But the real reason is if a field is only read in a method, only in the interpreter, and not in a method that is compiled, then the field is so unimportant, then it's not even worth counting it. So that's basically the interpreter is somehow our first level of filtering fields. And it's a really good filter because it greatly reduces the number of fields that we even have to count. So it reduces the overhead.
How much of a difference of impact was there just from doing co-allocation versus collocation plus inlining?
In terms of performance?
Yeah.
I have the performance numbers later on then. So what is the garbage collector doing? Basically, when copying objects, it's quite easy to copy objects, the whole group together. So instead of copying a single object down, we copy the polyline, the array list, and the object array together. And even if they are not co-located in the heap yet, they are copied together so that they end up. Of course, there can be corner cases when the garbage collector sees the array list first, and then it copies that down and cannot co-locate it. But that's solvable in the garbage collector with some tricks to just mark the child objects with a certain flag and then delay the copying. So these are just tricks in the garbage collector to really co-locate the objects as much as possible. And when we do a full collection in the mark and compact collector, it's really guaranteed that every co-location can be observed. You might have noticed that my first slide with the object graph that the child objects were at the top of the parent object. So basically, it's some sort of a reverse order. Why do we have that? Basically, what we want is when we have an object and the child object, we want to do an access of the field size, for example, with a fixed offset from the pointer to the polyline object. But when we have class hierarchies, then basically the subclasses fill these slots at the end of the object. So you cannot have a fixed offset for the size field when you have a class hierarchy. And just reversing that order was a quite convenient solution for that, because now basically you have subclasses of polyline extending to the bottom and object inlining extending the object to the top, and we have fixed offsets. The only thing that we cannot do is we cannot allow subclasses of array list here, so we cannot now have that this object is bigger. But that's not happening anyway because we have to allocate the polyline and the array list together. So we have to fuse that allocation together, so that wouldn't be allowed anyway. So that's the reason for this reverse object order. Co-allocation, that's also done in the just-in-time compiler. And the only thing that we have to make sure is that the allocation of the polyline, the allocation of the array list, and the allocation of the object array end up in the same compilation unit, which means they have to end up in one JIT compiled method, which is obviously the top-level allocate method. So we have to make sure that these constructors are all inlined, otherwise we cannot co-allocate it. So the first good news is that constructors are usually small, so the inlining happens anyway. And the second good news is when we know that we want to do co-allocation, we can just tune our inlining heuristics so that the constructors are inlined more aggressively, so that we can make sure that all these separate allocations end up in one JIT compiled method. And then it's basically the three new instructions are fused to one co-allocation instruction in the JIT compiled method, and there's only one big chunk of memory allocated. That's, again, a compiler transformation. And yes? Yes?
So once you do this co-allocation, does the garbage collector sees it as a single object, or does it still see it as three different objects?
The garbage collector sees it as a group of objects, which means the individual object headers are still intact. So we do not remove object headers. So you have this object header, this object header, this object header. The first reason for that is that you have the pointer in here. That's the main pointer to the polyline object. So you cannot really remove this header because that would mean that something starts in the heap without the header. That would be somehow weird. And the other reason is we still have the interpreter executing some methods. And by keeping all the headers and even all the field pointers intact, we can let the interpreter run unmodified. So the interpreter can still access the field, follow the pointer to the array list, follow the pointer to the array, and do a normal array access.
So that means that there's a new concept in the GC for these groups.
Yeah. So basically we have a concept of groups in the GC. The GC sees that's a polyline and looks up the metadata and says, oh, there should be 2 other objects collocated to it, and then copies processes 3 objects at once. But when you just look at the heap, these are still different objects.
So just one other question. In the HotSpot compiler, when you do object layout, it's only one directional growth for subclasses, right? It's not a bidirectional class layout?
Yeah, it's just growing
Okay.
downward in one dimension. Field store guards. That's one example where a guard is necessary, because yes, it could happen that someone allocates calls the constructor of polyline directly without going through this inline method, this method where the co-allocation happened, and in that case you cannot fuse the polyline and the array list together. So we have to make sure that this pass is not executed. It's highly unlikely that it's executed. But it could be. One example is when you use reflection to allocate an object, then that's a thing we cannot process with our co-allocation, or if GNI, the Java native interface, is doing stuff. So we have to support it. So we cannot just say, we cannot just disable reflection for our classes. That would violate the specification. But we can assume that no reflection happens, and that's the common case. And if reflection happens, then the field store guards triggers and the optimization is undone. So all these dynamic features of Java, of managed languages, are handled via deoptimization. And then finally, as I said, doing really the address arithmetic, that's the easiest part. For example, when we access a field, so they get points, then it's just doing some address arithmetic, subtract the object size, and you basically have the beginning of the array list. Some very neat trick is then the same thing for arrays. Basically, arrays have the problem, and I don't want to go into all the implementation details of that, just to mention it briefly. The array list is a dynamic data structure. So saying that the element data field is never overwritten, that's some sort of too conservative, because it's inherent in the array list that when elements are added, this array can grow. But fortunately, we have the array bounds check, and what we can do is when the object is overwritten, we have our duplicate length field that we then set to 0, which means an optimized array access triggers an array out of bounds exception, or not really an exception, but the slow pass is triggered because our special length is set to 0, and then we take the slow pass and access the array as before using this pointer. That's another reason why the field pointer is still present. It's just our backup for arrays that are overwritten. And then the next garbage collection puts this object here again, and we are fine. So basically the garbage collector collocates the objects again, and then the array accesses after the GC are then optimized again.
So wait, that means that the offset to the elements of the array are actually dynamically computed.
Yes.
They vary. So why is the collocation even useful? Because I need to read the size field anyway to compute my offset, so I might as well read the pointer.
Yes. The reason is that's basically the measuring code, and you have to read the array length in any case because you have to do the array bounds check. So you cannot save the access to the array length field unless you can really statically prove that the bounds check is unnecessary. So you have the access to the array length field, and basically with some what you can do is fold this address computation into the Aerie bounds check by changing the bounds check to not using a compare but to using a subtract instruction that does the bounds check and the address arithmetic at once.
So because you have to read the length anyway,
Yeah.
bounds check, you then use that to compute the offset.
Yeah.
Okay.
So yes, when you do a PhD, you have to do some crazy stuff too, so that. But it works, and it really fulfills all the specifications of Java. And that's the evaluation. So what's the bottom line? We have the baseline. We have the green bars are just object collocation, so that's just the benefit of the better cache behavior. Orange is object inlining, so only do it for objects, and the red bars are then also do the full stuff with the address arithmetic for optimizing arrays. And basically for the benchmarks, we measured the first run and the steady state run. So the lower bars, these are the first run, and the upper bars are the steady state run. What do you see? First, depending on the benchmark, you really can get a big speed up. Yes, I know the DB benchmark, it's somehow questionable if that's a realistic setting, but it's always great for evaluating such sorts of optimizations because that's really the example that I showed in all the slides. You have your data object, you have your array list, and you have your array. That's exactly the thing happening here, and you get a huge speed up. And the interesting stuff is you don't have to optimize many fields. So for that benchmark, basically in total 8 fields were optimized. For that benchmark, 4 fields were optimized, and you still get a big speed up. You get the speed up always for the fast part, for the steady state. So after applying all optimizations, since we have the read barrier and the increased compilation overhead, the first run of some benchmarks gets slower, and that's just your startup overhead for applying all the optimizations. And that's a thing that you could improve by doing a more clever compilation scheduling. So we didn't really optimize that because in many cases, even the first run, as though the optimization succeeds early enough so that the first run also benefits. But yes, it's something that you have to do during the startup of the application, so some benchmarks get a hit there.
A very low benefit of co-allocation in these benchmarks. That's surprising.
Yes, the cache behavior, the only benchmark really benefiting is the DB benchmark because it has so many small objects that are accessed frequently, so the cache behavior matters there. But overall, the cache behavior is not the biggest impact. So really eliminating the memory access, which means that you don't even have to access the parent object.
I'm just kind of curious comparing to Trishul's work on co-allocation, where he's obviously very important. I'm guessing maybe it's actually because there's a garbage collector, co-allocation falls off. I don't know. Like, I don't know if you have a thought on it. It's just like I'm kind of. It's sort of surprising.
Is this maybe a function of the benchmarks not being really representative of real code?
Yeah, exactly. That's why, like, maybe DB.
Well, that's the. You can argue that the DB benchmark is not realistic, but the MTRT, that's a multi-threaded ray tracer, that's a real piece of Java code. So that's a real Java application that went into the benchmark. So that I would consider that a real realistic. But yes, the cache behavior was not the biggest impact. And Jack, that's a parser generator. So that's the old name of Java CC.
So I know Catherine McKinley had a student working at trying to do some of the work like Trishul was doing with object location for cache locality, and she had a hard time with the spec benchmarks too, trying to get performance because of that. And I think they had a better time with the decapo benchmark. So if you have a chance, you should try this on decapo.
Yeah, so we did it for the decapo benchmarks. For the decapo benchmarks, basically, you cannot gain such big speedups because the benchmarks are really bigger. So the most you get for the capo are 5%, I think, was the maximum. But you still get a speed up, and it's a production quality VM, so getting 5% speed up, I would say it's not bad. But we did it, and you can look up the exact numbers in the paper afterwards if you're interested.
But I think that's sort of what I was trying to point out. Your baseline is already a very good compiler.
Yeah.
And so maybe HotSpot already does do any kind of optimizations related to layout or GC related?
No.
It doesn't do anything like that?
So that HotSpot doesn't do anything in that direction yet.
And it is
So
Well, to be fair, right? I mean, moving collectors usually gets some co-location benefits
Right.
without trying.
Right. Yeah.
But there's nothing.
Say,
What's that?
which is
Yeah,
Trishul's work was on C, right?
yeah, that's why I thought having a collector changed that. And then I'm also kind of wondering at the same token, like the speedups we're seeing from array inlining, like how much of that is really subject to the benchmark? Like if you do array inlining on the capo, do we actually even have this sort of problem?
On the capo, everything is scaled down, but it's still somehow the same pattern that collocation gives you a bit, object inlining gives you more, and array inlining is still some more speed up.
So, but is it like, oh, I'm going to get 74% or I'm going to get 30% from inlining, or is it not?
No, it's you get 5% or so. One thing that we unfortunately cannot optimize with that system, but we did it separately later on, are strings. So the string object and the character array. That's basically because the Java library has this sharing of the character array for multiple string objects. So we did a separate optimization that just did a transformation for the string class. And that gives you especially good results for the capo for some string-oriented benchmarks. So doing the collocation for strings is especially valuable and good, but we don't have it in this chart. Are there any additional questions?
Do you have overhead? Like, what is adding the read barriers provide above and beyond the default hotspot?
You mean in terms of overhead?
Yeah.
It's if you really have the read barriers on all the time, you would have for some benchmarks 50% slowdown. If you really have read barriers for all fields on all the time.
But presumably you turn those off after you use it.
Yeah. So
do you have the numbers relative to like a fifth bar here, which would be?
You see the read barrier somehow here. That's the read barrier overhead in the first run. At least until they are removed. So that's basically the read barrier and the compilation. That's the overhead you see here in the first run. Any other question to that topic? Because otherwise I'm switching over to trace-based compilation. And since you are doing trace-based compilation at MSR, I don't think I have to talk too much about the motivation for it. But basically, the whole runtime feedback-directed optimization approach is based on the assumption that you have many methods executed in an application, but only very few of them are really important. So that's the statistic for one of the SpecJVM 2008 benchmarks, where you see that only very few methods, so that's 50. So basically only 10 methods are really what matters in that benchmark. And you can say, oh, I can compile the first 50 and I get most of it. And if you compile 100, then you basically are done. But if you look into the details of these compiled methods, then you have the same distribution inside the method. So now that's, again, the methods, but counted the execution count for every basic block. And even the most frequent, the hottest method of the benchmark has only a few blocks that are really important. And the hottest method has 50 blocks, and some of them are basically never executed. So you have this distribution of execution frequency not only between methods, but also inside methods. So what you really want to optimize is only this set of basic blocks and not this set of methods. And that's exactly what Treys-based compilation is doing by just compiling the frequently used execution path. So Treys recording, basically, we have here a set of two methods, the left and right, and with the control flow graph, and that's a method called by the first method. And when you say, oh, that's my hot loop, then really only record these few basic blocks and call that a trace and really compile it as a linear list of basic blocks. Obviously, just one trace through a method is not really what you want. You want some sort of growing the traces on demand. So when you find out that a second pass is also frequently executed, just add it to the trace so that you get the trace tree. And that's basically the approach that Andreas Gall in Irvine did for his PhD work, and it's now in the TraceMonkey JavaScript engine of Mozilla. And it works pretty well, and I think Spur has the same approach. It works pretty well, but it has the problem of some sort of code bloat, that you duplicate too many blocks, especially when you have a complex control flow, and especially the complex Java benchmarks that we tried on. So we had the same approach also in a tracing Java VM. It turned out you get some sort of code explosion, and the worst case example you can ever construct is, of course, that you have a big set of ifs where every branch is basically taken with the same likelihood. So in that case, you would really get 256 leaves in the tree and huge amount of code compiled for that method. So what we then switched to in our Java-based implementation of tracing is to trace regions. So instead of doing this tree-based approach, stay with a more traditional control flow graph or trace graph that has the merge points in, for example, or even has side exits that are also compiled, so not only focus on the loop, but basically that eliminates the amount of code duplication that is happening. And I think that's really important, especially in the context of more complex applications where the loops are really long. So when you analyze the Java benchmarks, Da Capo or SpecJVM 2008, then this concept of just optimizing short loops doesn't give you enough coverage of the benchmark to get enough speed up. And the second problem that we encountered are these region exits. At some point, this region exit, so when you exit a trace and go back to the stuff that's around, basically in the interpreter or in the baseline JIT compiler, that's some sort of deoptimization again. That's exactly the same thing. You have to reconstruct the interpreter, stack frames, and go to it, jump to it, perhaps even reconstruct a bunch of interpreter stack frames if you had tracing across method boundaries, and it's expensive. So it's just not possible to use this general facility of HotSpot to reconstruct the stack frames from metadata for these region exits. We call them transfers, that are frequently taken. So you really have to optimize that, and that's the reason why we distinguish between fast transfers. These are really exits out of a trace that are taken, and these are optimized. So the compiler really generates specialized meshing code to reconstruct the interpreter state and direct jump then to the interpreter back. But it has a high compilation and memory overhead. And the slow transfers, that's the classic deoptimization approach. Just use metadata to reconstruct the stack frames. That's basically the safety net again, the backup solution for all transfers that are expected to be never taken. Like when you have Aerie bounds checks, then you expect them to not fail. When you have null pointer checks, you're not expecting them to fail. And even with some sort of profiling, you can basically reduce the number of fast transfers that you need to a really small amount so that the code overhead isn't prohibitive. Some benchmark numbers also for our Treys compiler. That's implemented in the Maxine VM. That's Sunlab's Java VM written in Java. That's a very recent project of Sunlabs, so Maxine itself is not heavily optimized yet and not completely stable. So that's basically targeting a moving system, and they are doing improvements to make it stable. We are doing our work. So these are, let's call it, rather preliminary numbers. But what we are comparing here is the baseline. That's only using Maxine's baseline compiler. So Maxine has a compile-only approach. There's no interpreter. There's only a baseline JIT compiler and an optimizing JIT compiler. So when you have the baseline, that's only using the baseline compiler. The red bars, that's using the traditional method-based compilation approach. And the green bars are our trace-based compilation approach. So, and the important thing to notice is that with the green bars, we are compiling far less code. So you have to keep in mind that the difference between the red and green bars is that the green bars, that the amount of code compiled is much lower, but still you get comparable performance. So for some benchmarks, it's much better. The reason why it's so much better for these benchmarks is that these are mathematical benchmarks that basically have one long-running loop, and the method-based JIT compiler doesn't do on-stack replacement, so it cannot kick in, whereas the trace-based compiler has on-stack replacement built in by design, so you get that for free. Yes?
These terms include the overhead of compilation?
Yeah, that's basically the whole system. So running just timing from the beginning to the end of the benchmark execution. But the compilation overhead is, since these are longer running benchmarks, the compilation overhead is not so big here. Especially for the mathematical benchmarks, you can neglect it.
So I wonder what so you're doing these region-based things for Java. I wonder how this would change for a language like JavaScript, where one of the wins that you get from Treys is that the different duplicates of the code can be specialized to different types. Yeah. Whereas with Java, you're already strongly typed. And so the chances of you saying, oh, I have an integer half the time and then a string the other half is far less common.
Yeah. So you're right, when you merge the code, when you have merge points, then this merges the type state again. So you have to make sure that this doesn't hurt. But also the difference for JavaScript is that at least the JavaScript benchmarks that are out right now are really only this small loop, so you don't have this big code bloat. Where you can, of course, claim is that valid for the real applications that are out on the web. That's a problem that needs to be solved first before we can really discuss that. But the additional type information that you get from Treys compilation, you somehow have this also in Java, because you also basically specialize on the types that you see during tracing. It's just there that types in Java are even more stable than in JavaScript.
So wouldn't Python be an example of where I would expect this branching stuff to be more important? While something like FFT, where we see tracing does worse, while FFT is somewhere where I would expect less divergence, yeah, tracing does better. So I don't know, just somehow the benchmarks again don't seem to agree with
So as I said, the numbers are very preliminary, and what's really hurting Maxine currently is garbage collection. So the reason that you don't see so much difference at these benchmarks is that a high percentage of time is spent in the garbage collector, so your code improvements don't kick in so much because the garbage collector is not optimized.
Kind of further out, like how far do you think this will take us beyond what method jibbing or whatever will take us?
What I think, and that brings me to my next slide, what I envision for trace compilation is I think we really need the most flexible trace regions. So we shouldn't limit ourselves to loops or anything. It should be really driven by profile information. So especially for Java, where you have long loops and sometimes really virtual method calls that you cannot trace because there are too many callees. So you need some sort of method-based compilation, method granularity, but you can still trace some methods. So just start tracing at the method entry and do your tracing as normal. And doing some sort of hybrid with method-based compilation is also perhaps not bad, especially when you have this trace regions with merge points anyway. Your trace compiler is not really different from a method-based compiler. The only difference is what you feed into the compiler. So you can have a front end of a trace and a front end directly from bytecodes, and that way you can solve the problems for recursion that are not really traceable, or you can construct recursive cases where trace compilation fails and where trace compilation by principle cannot really optimize it. So some hybrid of flexible tracing regions combined with a real method-based compiler might be the way to go for that. So I think not focusing too much on loops is bad, and having flexible merge points is necessary. Another thing is this overhead of tracing. So the trace compilation, like we do it for now, is really generate the instruction in the interpreter or in the baseline JIT while recording, which means you have to really make sure you don't trace anything that you can later not compile, because that would be an overhead that you cannot where you cannot get the benefit then later on. So what we are trying also is do not create instruction during tracing, but just record the list of blocks, the list of instructions that are encountered. So doing some sort of hybrid between path profiling and trace recording. And if the benefit that you can have the trace recording on for a long time, long means a few thousand executions of a method, and really collect all the traces that you found, count them, and then feed that into the compiler to optimize it, and only at that point create the instructions. I think that's at least an approach worth trying. Unless we really have tried it, I cannot claim it's better or worse, but my intuition says that it can have some benefits. It has the downside that you have less type information and less actual information during recording available in the compiler, so you cannot collect as a type profile as good as when you really create instructions during recording. And to try out all this, there is currently a project going on in Linz again, where we try to do a trace compiler for the HotSpot VM. So basically take the client compiler of the HotSpot VM and give it a different front end that gets in traces from a trace recording phase, and see what we get from there. And there, since we really have a full-fledged method-based compiler that we are based on, we have this ability to compile arbitrary control flow, and we will see how that works out. But that started this summer, so there are no results from that yet. But I think it's interesting to see. And I think Treys compilation has the potential of really reducing the compilation overhead, but tuning it in the right way, that's still an open question. And another open question, to just broaden the talk again at the end, is how do we want to deal with virtual machines in general? Because what I don't like currently about VMs is that they are always so focused. So you have the JavaScript implementation focused, and yes, do everything you can do to optimize JavaScript, and then have a completely different Java VM, or whatever language you mean you want to optimize for. I used Ruby in these slides because the name is shorter than JavaScript, so it was easier to fit here. But feel free to use whatever name you want. And basically, these are the two approaches that we have currently, either completely separate VMs or this layered approach where you have the dynamic language VM running on top of the static language VM. There are basically many dynamic languages that have implementation on top of Java and equally on top on the .NET platform. But that's the layering. It still allows some interaction between statically and dynamically typed code, but not a complete interaction. And the main disadvantage is that this VM is really complicated for itself. When you generate Java bytecodes or .NET bytecodes, that's some sort of weird setting where you first translate your dynamic language to statically typed bytecodes and feed that into a JIT compiler for statically typed bytecodes down here, and not the best for optimization.
Wait, what's wrong with that?
Well, at first you have to do a JIT compiler here, and you really don't want to do that. And you're talking about Spur? Yeah, I know. You're already somehow in the middle of what what I'm talking about. I know that you, with Spur, you have a different thing, but when you think of Iron Ruby or Iron Python on .NET, that's exactly that approach. So with a Treys compiler, you can do better things. You can do it either your way, that you have the runtime in C# or so and trace it together, or what we tried out a bit is you have a VM with a tracing compiler here, but and only an interpreter here, and instead of the Treys compiler optimizing the interpreter, you teach the Treys compiler to really optimize the VM, the application running on top here. So basically, you tell the Treys compiler, this is my interpreter loop, so don't use the interpreter loop as the granularity for compilation. Use the loops inside the dynamic language application as your granularity of compilation. So basically, the interpreter serves some sort of implicit specification of your language. So you have one JIT compiler here that uses the interpreter to really optimize this code without any intermediate steps and any overhead. But what you really want is some sort of a modular VM, I think, where you have a common set of things that are common to all VMs, then specialize it for the semantics of your different languages, but then have one big application that can somehow freely mix the code. So like a thing that you have browser written in C# and that's executing JavaScript code, but from the point of view of the VM and the optimization system, there are no boundaries, so you can trace or compile inline across the different languages. So that's, I think, a goal that we should try to reach, because it can really unlock the benefit of this VM-based execution model. And then you can really do good profiling here, do feedback-directed optimizations here, do optimistic optimizations for the whole application that consists of many languages. And then we don't have to think about what do we implement in what language. Just use whatever mixture you think is best, and the VM just optimizes everything together.
So where would you put spur on this?
Where would I put spur on that picture? In the middle?
No, it's not the right box.
That's
spur.
It somehow has concepts of many of these boxes, I would say.
No,
so
that's just that one box up there.
this one?
No,
Only
because,
that one.
no, he said that JUruby VM has a jitter. We don't have a jitter.
I think you
So
misspoke when you
that's
said
not
jitter.
spur.
So
You only have a runtime.
yeah, you only have the runtime here, and you have a Treys compiler that compiles everything. So that's somehow already part of that box. So spur is somehow. It's not that you have this black and white scenario that these are the 4 things that you can make and you cannot make anything in between. It's just, I think both of the approaches that are deployed in product currently have their problems. So it's, I think we as researchers should try to come up with solutions that really foster that integration of languages and combined optimization, combined execution. So that the developers, so that we don't want to tell the developers, oh, you can either do it in Java, then it's fast, or you can do it in JavaScript, then you're flexible and you're customized. What you really want is an application that has a core of a statically typed language, because it's easier to reason about that and to get it correct, but then allow customizations in a dynamic language, in a domain-specific language, and mixing that all together in VM. That's really the benefit of the VM-based execution model. So I think that's something we should think about.
Perspective is like, okay, go back to the scheme world. They have their JIT for their full thing, and have all sorts of languages running on it. Like they make a new language every week, and they all talk to each other.
Yes.
And we so do not care.
It's just kind of, we already have that world.
Yeah, but in scheme, it's not really that you really have one VM and that is flexible to do everything. You don't have these specialized modules. It's more using the inherent semantics of the language to do that, and not really.
So what would be the specialized module?
Well, when you really say you want to fuse Java and JavaScript, you still have the Java specification with all of the call semantics and the memory model and the object model that you have. You have to fulfill that specification, and you have to fulfill the JavaScript specification. So there are differences.
So they're specialized in that they have semantic, interesting semantics, but not actually interesting performance specialization.
Yeah, but the JIT compiler, basically the real core optimizations don't really care what they're executing. So they don't have to know about these special things. And doing a garbage collector, for all languages, it's a bit more tricky, because JavaScript, you have completely different object model to Java, but still you can get some sort of combined execution with that. So at least I think we should give it a try. Yeah, and with that, any additional questions left? I'm glad that you were interactive, so thank you.